It can be a good research topic for students to find uses of induction. So here are just a couple to illustrate what a range of devices there is. One is the electric guitar. The metal strings are magnetized by a permanent magnet in the pickup coil, which is under the metal plate you can see below the strings. When the magnetized string vibrates, it induces an EMF in the pickup coil. Another use is the ground fault circuit interrupter, also called the safety switch. Normally, the current to any device equals the current out of it. So if the wires carrying the current to and from an appliance in your house are put through an iron ring, the magnetic fields those wires create are equal and opposite. However, if there is a ground fault, which means that some of the current is leaking to the ground, maybe through the metal casing on a device, the return current will be less, so then there is a net flux through the ring, which then induces an EMF that can be detected and set off a circuit breaker. This can be triggered by very small currents, so it's more useful than the standard magnetic circuit breakers, and the response time is less than one complete cycle of the AC power, which is a 50th of a second. That means that this time is short enough to actually save someone's life if they were getting an electric shock. There are plenty of other uses of induction that you can research, including the induction motor. This is an extremely useful type of electrical motor because it relies on induced current in the central coil, which then needs no electrical contact with the external circuit. So there are no brushes where the moving part has to brush against the stationary part, and those brushes are the weak point of any motor. So induction motors are very reliable and safe, though not particularly high torque motors. One of the most important applications of induction is the transformer. Transformers are used to increase or decrease AC voltage. It only works with AC because you need a changing magnetic flux to induce an EMF. And in transformers, the changing magnetic flux is achieved by having an AC power supply. A simplified version of a transformer is shown here, with two coils around separate sections of an iron ring. In real transformers, the coils are wound on top of each other to save space. So you have the primary circuit with the supply voltage Vp that you see on the left, and it has Np number of turns. The secondary coil, which is the one without the power supply, will have induced EMF Vs, meaning voltage in the secondary, and it has Ns number of turns in that coil. The same magnetic flux flows through both coils, because when the iron ring is continuous, the magnetic flux will be contained within it, and very little flux will leak out into the air. So we can analyze it like this. According to Faraday's law, the supply voltage induces a changing magnetic flux phi in the iron core. We assume that the flux induced from the primary is the same as the flux through the secondary coil. Using Faraday's law again, that changing flux induces the secondary EMF, and the ratio of primary to secondary voltage is equal to the ratio of the number of coils in the primary and secondary circuits. So this is called the transformer equation, and it tells us that the primary voltage over the secondary voltage is equal to the ratio of the primary number of coils over the secondary number of coils. So if there are more turns in the secondary coil than the primary coil, then the secondary voltage will be bigger than the primary voltage, and that we call a step-up transformer. If the number of turns in the secondary is lower than the primary, it is stepping the voltage down. Because we often want to change voltages, these are extremely useful and widely used devices. Many devices can't use the 240 volts AC that we get from our power points, and some can't use AC electricity at all. So transformers are needed to firstly change the voltages as necessary. Then rectifiers might also be needed to turn AC to DC. One example is the household computer. That will need a few separate power input lines with different voltages. So 12 volts might be needed to run the disk drives and the cooling fans, while the logic circuits need 5 volts. One other device that needs a high voltage is a microwave oven. That runs on mains voltage but has to step it up to 5,000 volts. Plasma TVs also need step-up transformers.